SwayamPrabha. Digital India. Educated India.
Hello and welcome everyone to today's lecture in this series of lectures on the modeling of multiphysics system. So, just a reminder that we are going over this segment on solid mechanics. We have already covered 3 lectures in which we have looked at different aspects of the solid mechanics problem. We have seen the relation between the strain and displacement in the lecture 1. Then we have seen the relation between forces and stresses and the conservation equation, that is conservation of linear momentum, in the lecture 2. In the last lecture, we have developed a correlation between the stress and the strain, in other terms the relation between the stress and the displacement. These have been the 3 parts we have taken. So we are considering something that is tangible, like the displacement or the deformation, to something that is tangible like the traction or the surface forces, into an equation or a governing equation based upon the conservation of linear momentum, in which we have the stress, which is a tensor coupled with the body force in equals to the mass times or the density times the acceleration. So, our acceleration is the second derivative of the displacement or the deformation with respect to the time, but our stress term is something we do not know. How to relate the stress to this displacement. In the last lecture we have seen that we use constitutive models, and these are material based models in which we can relate the different aspects of stress, that is our longitudinal stresses or our shear stresses, to the longitudinal and the shear strains based upon the nature of the material. So, we had left all the way up to understanding these for a plane stress and plane strain in 2 dimension. Our models were dependent upon something that we were calling an isotropic linear elastic material. Isotropic meant that it was uniform in all directions. It was linear, that means that the stress strain relation is linear. It is elastic, means that it is able to come back to its undeformed state on the relaxation of the stress. Okay. Now we will go on to some brief definitions on a general anisotropic linear elastic material. Again, it is linear elastic in nature, which means that the stress strain are reversible. That is, if you relax the stress, the strain should be able to come back to its original state. However, they are general anisotropic, which means that they have some direction dependence. Okay, before we start that, we have defined 2 tensors, the stiffness tensor and the compliance tensor. Are 4th order. So, these are 4th order tensor. So, the stiffness tensor is given byCijkl and the compliance tensor is given by Zijkl. So, we have these 4 terms. Each of these terms can go from 1 to 3, and that means that we have a 3 cross 3 cross 3 cross 3 matrix, and which will have 81 components. Now, these are too many components to handle. Right, 81 components matrix itself becomes very cumbersome to deal with, and we need some way in which we can resolve this, right, some way or some direction in which we can simplify this 81 components down to something that is justifiable in a practical problem. It is not possible to measure 81 constants by varying each direction of stress. Now, thankfully, our stress tensor and our strain tensor are symmetric. Our infinitesimal strain tensor epsilon 1 epsilon 1 epsilon 2 epsilon 2 they are symmetric in nature. So, 1 2 is equals to 2 1, likewise for the stress. That is one degree of symmetry. The second symmetry comes from the definition of the strain energy. We have looked what is strain energy and how the stress and strain can relate it to the strain energy. So, based upon that, we can come up with certain extensions of symmetry. So, if we just take our C, that is our stiffness tensor, thenCijkl is equals to Ckl is equals toCijkl equals to ij lk. So what did we do? First we flipped the first two with the last two. So 1 2 is flipped with 3 4. So instead of 1 2 3 4 we have 3 4 1 2. Then we have flipped the first two. So we have 2 1 3 4, and then we have flipped the last two. So it is 1 2 4 3. So this reduces down our tensor to having 36 components. So in this case we find out that the first two symmetry, that is C I j k l is equals to C k l I j is due to the definition of the strain energy, and the last two, the first with this third, are from the symmetry of the stress and the strain tensor. Okay. So with that definition in mind, we have now boiled down our 81 component matrix down to a 36 component matrix, which relates 6 component vector of strain to a 6 component vector of stress and vice versa. Okay. Now most of these material properties and how many constants do we need depend upon the type of material that we use. And every material is different. This is a plastic, it is amorphous in nature, which means that all directions are equal. And most likely its property is equal in all direction. Likewise, you can have material which can have preferential direction in one axis. So one axis can be stronger than another, and all of these, this comes from the crystal lattice. So material behavior plays a crucial role in determining the elastic properties. Okay, so it is, or the constitutive laws itself is material driven. These are done by experiments. You do an experiment, you measure the strain for a given applied stress, and based upon that you try to get out these constants. Some materials can have 2 axes of symmetry, some can have 3 axes of symmetry. Based upon the axis of symmetry, you are able to reduce the number of constants that you do need, and our Cijk, that is our stiffness tensor, or our compliance tensor, likewise can be modified and can be simplified. So let us take the first type of material. There are a lot of materials based upon their crystal lattice and structure. We are taking a couple of examples. So for example, an orthotropic material, right. So these have 3 mutually perpendicular axes in their crystal lattice. Or planes rather than axes. Okay. So since they have 3 mutually perpendicular planes, we also have that their values may be different. So in this case we will have 9 components or 9 constants that we need to derive. So S for this will be 1 by E1 minus nu 2 1 by E2 minus nu 3 1 by E3 1 by E2 minus nu 3 2 over E3 1 by E3. Okay, and this will be symmetric. This lower half will be symmetric. Then we will have zeros in these 2 quadrants, and we will have 1 by mu 2 3, 1 by mu 1 3, by mu 1 2, and again these 2 will be equals to 0. Okay, so this is our S I j k l. We have 9 constants that we have. So we have E1, E2, E3. We have nu 2 1, nu 3 1, nu 3 2, and then we have mu 1 2, mu 2 3, mu 3 1. These are 9 constants that we have to use in this case. All right. Then we can have another type of material, and say we have a transversely isotropic material. So, what a transversely isotropic is, that it is an orthotropic solid. So, it is an orthotropic with one plane of symmetry. So, about one plane, the left hand side and the right hand side is symmetric, and that is one plane of symmetry or one plane of isotropy. Okay. In this case, our S will be, so we have now two planes. So, EP minus nu P over EP minus nu TP over ET 1 by PP by ET minus nu TP over ET. These are all zeros. They are all zeros. So, 1 by mu T by mu T. So, we have now 6 components. So, we have reduced 3 components by imparting the symmetry. So, from 9 components we have boiled down to 6 components. What are the components? We have EP, ET, nu P, nu TP and mu T. How many we have? Let's write down. I think I am missing one. ET, nu P, nu TP, mu T and mu TP. We should have mu P. We should have one more. Which one should it be? So, this should be mu T, the perpendicular plane. Okay. Please do check this one more time, and always refer to the Applied Mechanics of Solid. By Alan Bauer. Okay. So, there should be 6 components of symmetry, 6 components that are required to define a transversely isotropic solid. There can be other types as well. We can have cubic. If it is cubic, then we have 3 components dependent. So, those will be for a cubic material will be 1 by E, 1 by E, 1 by E minus nu by E minus nu by E minus nu by E, and then we will have 1 by mu, 1 by mu, 1 by mu. So, we will have E, nu and mu, where mu is the shear modulus, E is the elastic modulus and nu is the Poisson's ratio. Okay, so these 3 will be the components for a cubic material. So, cubic material will have 2 planes of symmetry, right? All the 3 planes are symmetric. So, if all the 3 planes are symmetric as well as it is isotropic, then we will have just 2 constants, and that is our linear elastic material with an isotropic assumption, right? So, we had this E and nu. Our shear modulus was dependent upon E and nu. So, E over 2 1 plus nu, that was our shear modulus, right. So, this is how we are going down in the number of components. So, a triclinic material, if I am not very wrong, has no directions of symmetry. All the angles are different, all the planes are different. You might have all the 36 components separate, right. And as you increase the symmetry in the crystal structure, and as you try to impose isotropy, you will see that the number of components that you need to determine reduces, and your stiffness tensor becomes simplified. Okay. Now, if we talk about generalized Hooke's law, then so far our Hooke's law has been determined based upon infinitesimal deformations. So, we had our Cauchy stress was equals to our Lagrange, our material stress and our nominal stress. Our Lagrange and Eulerian strains were boiled down to the infinitesimal strain. So, let us rewrite what we had written earlier in terms of strain. F of ij is delta ij plus del ui by del xj. Was our deformation gradient. Our Lagrangian strain was 1 by 2 f of ki, f transpose f of kj, f minus delta ij or minus I, that is our Lagrange strain, and then our Euler strain is 1 by 2 delta ij F inverse Ki, F inverse transpose minus F inverse Kj. Okay. So, this was our Lagrange strain, and this was our Euler strain. Okay. Now, we also had a couple of definitions of stress. So, let us first, if we talk about Lagrange strain, then the material stress, that is also called the pK2 stress, is related to the Lagrange strain. So, sigma ij is equals to C ij KL into E KL. Okay. Please remember that the material stress, it was the force projected from the deformed state to the undeformed state, and the area that we had taken was also on the undeformed area. So, it was a projected force over the undeformed area, right, and since we are taking the reference to the initial frame of reference, so in that case we will also take the Lagrange strain rather than the Eulerian strain, because Lagrange strain is with respect to the initial frame of reference or the undeformed frame of reference. The second one is our Cauchy stress. So, our Cauchy stress is related to the Eulerian strain tensor. So, sigma ij equals to T C star ij KL epsilon star KL. Again, C and C star are in two different frame of reference. They are still the material driven property, however, the frame of references are different. So, we need to do some transformation from C to C star. Okay. So, if you want to make this transformation between C to C star, we know that sigma ij, that is our Cauchy stress, is related to the material stress, that is a pure Kirchhoff stress, as 1 by j of F I k sigma KL F of JL. Okay. So, we can then substitute sigma by this term, we can then replace the terms into this tensor, and we do some algebra. We can find that C star of I j m n is equals to 1 by j F of I p F of j q C of p q K L F of K M M K F of N L. Okay. So, this is a transformation to transform from our deformed frame of reference the undeformed frame of reference. Right. So, you can make that transformation if needed. If it is an isotropic material, then we can say that sigma ij is E over 1 plus nu E ij plus nu over 1 minus 2 nu E k k delta ij, and sigma ij will be equals to E over 1 plus nu E star ij plus nu over 1 minus 2 nu E star k k delta ij. Please remember one thing that we had talked in last class is that these material properties like the elastic modulus or the Poisson's ratio or the other material properties like shear modulus and all, they are not dependent upon the frame of reference. They are material properties, they are dependent upon the type of material, but they have no dependence on the frame of reference that we are using. Okay. With that understanding, we have covered up three main segments of our solid mechanics. So, if you remember the points that we wrote in lecture 1, or if you have not seen the lecture 1 for the solid mechanics, I would suggest you go back over there. Is that we had the first segment was to relate the deformation to the strain. We had different definitions of strain. The second lecture or the second component was to have a definition of force or traction related to stress. And we had seen different types of stresses and different definitions of stresses and how they can be related to the different cross section areas or the different frame of reference. The third point was to derive a conservation equation, and that was based upon the conservation of momentum, either linear momentum or angular momentum. And we had an equation or an expression which related the stress to the deformation from our conservation equation. And the final fourth segment was to have a constitutive relation or a constitutive law which can relate the stress to the strain, or in terms the stress to the deformation, because deformation is something we can tangibly measure. That was our fourth step, and that is what we finished up to this point. So, now we have all the 4 steps ready. The last part is to combine everything together and to have one equation or one expression which will be entirely driven by the displacement of the body, and we will have some boundary conditions based upon the surface traction or the surface displacement. Right, that was our objective, and this is the final modeling step for any solid mechanics problem. Okay, so we are bringing everything together. Let us just revise what we had. So, we had our displacement strain relation, displacement or deformation, which was we are just talking about infinitesimal strains for now, del ui by del xj. If you remember also from our Einstein summation notation, I think that was in lecture 1, right? Yes. So, and as well as in lecture 2. So, 1 by 2 we had said that we can put derivatives as comma. So, I comma j plus u j comma I. Okay. The second was our stress strain relation. So, this one we had said that sigma ij was equals to E over 1 plus nu. This is for a linear elastic isotropic material of epsilon ij plus nu 1 minus 2 nu epsilon kk delta ij minus E alpha delta t over 1 minus 2 nu into del ij. Okay. In general, sigma ij is equals to C ij kl epsilon ij minus alpha delta t. I am sorry, this should be kl, epsilon kl delta kl. Okay, with C ij k will have the components of the stiffness tensor. Okay, then the third one was our governing equation or a conservation equation. Which stated that the gradient of the stress tensor, let us write it in terms of I. Okay, and the rho aj is del square uj by del t square. This is our conservation equation. Now, in this conservation equation, we have a second order derivative with respect to position. So, we need 2 initial conditions, and we will eventually come up that we will have a second order derivative with respect to space for the deformation. So, we need 2 boundary conditions. So, typically our boundary conditions can be of 2 types. So, we can have one in which the u at the boundary is equals to a constant u of I or u of j, however you would like to use u of j. This is a Dirichlet condition. And the second one is that the sigma ji dot with nj, which is our traction vector T of I, is a constant. So, we know the traction or the force on the surface, it is a constant. This is very close to a Neumann type boundary condition. Right? It might not be an exact Neumann condition, it's close to a Neumann type. This is called the traction boundary condition. This is traction and this is a displacement boundary condition. So, typical solid mechanics problem are defined either by a traction based boundary condition or defined by a displacement based boundary condition. So, you either know, for example, this pen, if I fix this end and if I pull from this end, then the displacement of this end is 0. So, u at x is equals to 0 is 0 and u at x is equals to L. We do not know, but sigma at x is equal sigma dot n, that is a traction, T at x is equals to n, we know is a force per unit area on this wall. All right. So now we have these three terms together. So now let us assemble our equation. So assembly of the Navier's equation. It's a very elegant equation to do. Okay, so let's write down again. So del sigma ij by del xi plus rho bj equals to rho del square ui by del t square. Sigma ij is equals to E over 1 plus nu epsilon ij plus nu over 1 minus 2 nu of epsilon kk del ij minus E alpha over 1 minus 2 nu delta t del ij. Okay, we are taking a derivative of this. So, del sigma ij by del xi is equals to E over 1 plus nu. We have del epsilon ij by del xi plus nu over 1 minus 2 nu del epsilon kk over del xi del ij minus E alpha over 1 minus 2 nu del t by del xi del ij. So, we can make some small modifications. So, let us rewrite this again. So, 1 plus nu, this term let us keep it untouched for now, del epsilon ij by del xi. The second term, we have this del xi term and this del ij term. So, this del ij, we know that I and j can be replaced, I is equals to j only, it is 1. So, we can take this away and replace I with j. So, nu over 1 minus 2 nu del epsilon kk by del xj minus E alpha over 1 minus 2 nu. Again the same thing we can do, del t by del xj. This is sigma ij comma I. Let us put this back into our expression. Well, before we do that, we can also do one more thing, is we can replace epsilon ij by 1 by 2 del ui by del xj plus del uj by del xi. Let us replace this into this equation before we put everything back together. So, del sigma ij by del xi is equals to E over 1 plus nu 1 by 2. I am taking this derivative inside. So, just bear with me, del square ui del xi del xj plus del square uj del xi del xi. Okay, so this del xi we are taking inside this bracket and multiplying with both the terms, plus nu 1 minus 2 nu. So, it is del square uk del xj del xk, and the other term is the same, E alpha delta t over 1 minus 2 nu del t by del xj. Okay. So, we have this now long big expression. Let us see if we can couple a few of these terms. One thing to see is that I is a repeating index in this, k is a repeating index in this. Now, repeating indexes are added up according to Einstein's summation notation. So, we do not care what kind of repeating index we are using. So, we use I or we use k, we do not care, right. So, we can replace this k with I, as long as it is repeating, it is fine. Okay. So, let us write it down again, del sigma ij by del xi is equals to E over 1 plus nu 1 half of u. I am writing it with commas now, otherwise it is becoming very cumbersome. U j comma I plus nu over 1 minus 2 nu u I comma ij. Let's see, u k, and k is repeating, or j I am sorry, minus E alpha over 1 minus 2 nu del t by del xg. Okay. So far you understand what commas are, right? This is just the derivative of del square ui by del x j del xi. That's all I mean by commas. Any term after comma is derivative. Okay. Now we have this term same and this term is different. So we can club things now, start clubbing things together. Del sigma ij by del xi is equals to, we are now clubbing e to 1 plus nu, that is the first term, and then this term e nu 1 plus nu 1 minus 2 nu, we have u I comma j I plus e over 2 1 plus nu u j comma I minus E alpha over 1 minus 2 nu del t by del xj. Okay, now we are at some place. This term is given by mu, this term is given by lambda. Please refer to the last lecture. You will find that when we talked about bulk modulus, we have defined the shear modulus, we have defined the bulk modulus, and we have defined the Lame constant. So mu is the shear modulus and lambda is the Lame constant. Okay, again this is mu. So we will have our expression as mu plus lambda u I comma j I plus mu u j comma I minus E alpha 1 minus 2 nu del t by del xj. This is del sigma ij by del xi. Now let us replace this back into original equation. So we will have, let us write it down one more time, del sigma ij by del xi plus rho bj equals to rho del square uj by del t square. If we substitute this, we will have mu plus lambda del square ui del xj del xi del square uj del xi del xi E alpha 1 minus 2 nu del t by del xj plus rho bj, so rho del square uj by del t square. This big expression is our Navier's equation. Okay. So we have seen that all the things we have been doing up to this lecture 4, we are able to combine into one equation. Now this entire expression is driven by these deformation terms. U is everywhere, except we have these two terms. One is this body force. Body force is well known. It can be gravity, it can be due to some electromagnetic effect, it can be pressure on the entire body, and this gradient of this temperature, this is our thermal deformation term, right. So temperature driven deformations will only cause stress in the body if there is a gradient. That means that the temperature needs to be a differential. It cannot be uniform temperature. If a body is uniformly heated, if I have this body and it is freely resting on my hand as such, and I increase the temperature from the room temperature right now says 20 degrees to 40 degrees, and the surface is frictionless, then the stress state in the body will be 0. There will be no stress in the body, although this pen has expanded under the thermal expansion. So strain will be there, E is equals to alpha delta t, but there will be no stress in the body. And why will there be no stress? Because there is no restriction towards this deformation. Its natural state at 40 degrees is different from its natural state at 30 degrees. However, if the temperature is not uniformly risen, and say this region is hot, this region is cold, and there is a temperature gradient along any direction, In that case, some part will want to expand more, some part will expand less. If that is the case, then the part that is expanding less will be pulling the part that is expanding more, and vice versa. So, one region will be under compression and the other region will be under tension. Okay, so that is why we need this temperature gradient term. Now, let us rewrite this without this thermal strain. In many applications, we do not have temperature gradients or thermal strain. So, if we rewrite this expression again, we will have mu plus lambda del square ui by del xj del xi plus mu del square uj by del xi del xi plus rho of bj to rho of del square uj by del t square. Okay. This is our consolidated expression. We can now have boundary conditions. So, we need 2 initial conditions and 2 boundary conditions because the second order derivative is position and second order derivative is time. Can anyone tell me what kind of equation this is? What kind of partial differential this is? So, unlike our diffusion equation which had this first order time derivative and a second order position derivative, this has a second order time and a second order position. So, this looks more like a wave equation rather than a parabolic equation, right, or rather than a diffusion equation. So, this is a hyperbolic equation or a wave equation that the system will be oscillating from the time derivative. Okay. Now, let us move on to our next. We need 2 initial conditions. So, typically the initial position and velocity. And we need 2 boundary conditions. Which can be displacement type or traction type on the boundaries. So, we can either know the stress. Now, you would imagine that this equation entirely driven by the displacement or the deformation. How will a stress boundary condition be used, or how will a traction boundary condition be used? So, we know that the stress itself is related to displacement from this expression. We can replace this epsilon ij with 1 by 2 del ui by del xj plus del uj by del xi. If we dot it with the surface normal from both sides, we can then relate the displacement, which is a first order derivative with the position, to a value, right, and it becomes similar to a Neumann type condition. Okay. Now, we have completed our Navier's expression now or our Navier's equation now, and we have seen an entire range of equation, that is a second order derivative with position and time, which can be used to model a solid mechanics problem. Now, let us try out a few examples. We will start with a membrane. Okay. So, membranes are typically bodies in which the third dimension is negligible compared to the first and second dimension. Rather, instead of dimension, let us write direction. So, what I mean by that is, say that we have a membrane attached between 2 places. Say this is E1, this is E2, this is E3, right. So, E1 and E2, the body can have some dimension or some value. Say it can be a sheet or like this piece of paper, right. So, a piece of paper is a membrane. Its third dimension, that is its thickness, is very small or negligible compared to its length and width. Okay, if that is the assumption that you can take up, then it's a membrane. We have a lot of things that are membrane driven. Your drums on a drum board or a tabla, right? It's a membrane on the surface, the skin, right? Your paper is a membrane. Many of our films that we use, they have similar behavior as a membrane. Aluminum foil, for example, is a membrane, right? Its thickness is very small compared to its length dimension. So, if that is the case, what we can say is that there is no bending effect. And any thickness variations is negligible. Okay. So, the thing is not going to bend. Bending means that the top surface is under tension and the bottom surface is under compression. There is no bending, there is no thickness to account for bending, right. There is also no change in the thickness across the length, right? There is no pinching. It is uniformly thick and there is no bending. Although it's going to oscillate, say this is one mode of oscillation. Right. So, although it is going to oscillate, but it will be just stretching along the 1 and 2 direction, there will be no bending in the third direction. If that is the case, then we can have an assumption. With this assumption, this is our assumption. So, we can say that u1 is equals to u2 is equals to 0 and u3. So, u1 and u2 there will be no displacement along u1 and u2. And u3 will be equals to as a function of x1 and x2 only and time t, and it is not a function of x3. So, this is an important consideration to remember, right. The u3, this is our u3. So, our u3 will only depend upon 1 and 2. So, it will vary along the length and along the width, but will not vary along the thickness. Okay, all right. If that is understood, then we can start from a Navier's equation. So, from Navier's equation, we had rho ui double dot lambda plus mu. I am just replacing I with j from the last example. So, we are repeating with respect to I or j. Let's rewrite this. Plus mu of u, this was I, right. So, I comma j, this plus rho bi. Okay. So, this was our Navier's equation. Let us just quickly check one time. So, we had, you just replace I with j, I and j, that is correct. Okay. So, lambda plus mu and mu. So, in this expression we have I is equals to 3. So, let us write this. So, rho u3 double dot means second derivative with position is equals to lambda plus mu. Let us write this term. So, this will be del square u1 by del x1 del x3 square u2 by del x2 del x3 del square u3 by del x3 square plus mu ijj, right. That is del square u3 by del x1 square plus del square u3 by del x2 square del square u3 by del x3 square plus rho of b3. Okay. Now, u1 and u2 are 0. So, these terms become 0. u3 is not a function of x3. So, this term also becomes 0. Likewise, u3 is not a function of x3. This term becomes 0. So, our simplified equation from our Navier's expression becomes rho del square u3 by del t square equals to mu del square u3 by del x3 and del x1 square plus del square u3 by del x2 square plus this rho b3. To solve this, we need two initial conditions, and that is u3 at x1 x2 at time 0 is a constant, is a function of x1 of x2. That is our initial, say the body is not flat initially, it's initially some stretch or some dome is there, right. So, some initial condition, and u3 dot, that is our time derivative, is equals to g of x1 x2. So, our initial velocity is a function of x1 x2, it is not uniform throughout, right. and then we need two boundary conditions. So those will be u3 for x1 boundary and x2 boundary at 0. It can be some constant, again that is displacement boundary at time t, not time 0, at all time t. And we can have our stress sigma along the boundary can be a constant, it is traction. Okay, so we know the stress in that direction. Typical cases for membranes, we do not usually model traction based condition. We can include pre-stress, that is the membrane is stretched out tightly, we can include this pre-stress in the membrane. However, we do not include most of the cases our boundary conditions are displacement boundary condition, that is that the body can be fixed at that point is the most common boundary condition, right. For example, a drum, it's stretched from the side but is fixed at the side. So in most cases u is equals to 0 at the boundary. Okay. So in most general cases, in common cases, u3 at x1 boundary and x2 boundary the given time t is equals to 0. This is a fixed boundary condition. Okay. Let us take up two example parts for this. First is the case where membrane has a distributed load. So, if the membrane has a distributed load, we are taking a one dimensional membrane, so 1D membrane. So, we are ignoring x2, right, we are just doing with respect to, we are ignoring x1, we are just doing it with respect to x2 with a uniformly distributed load. Let us say the load is P, it is a pressure. We will have our expression. So, let us write it down, del square u3 by del t square, del square u3 by del x1 square, u3 by del x2 square plus this pressure term P. This is rho into B, so I have just multiply it with rho and this becomes a pressure term P. We are looking for steady state, at steady state. It can be some constant, again that is displacement boundary at time t, not time 0, at all time t. And we can have our stress sigma along the boundary can be a constant, it is traction. Okay, so we know the stress in that direction. Typical, this terms becomes 0, this term becomes 0, it is one dimensional. So, our equation becomes mu d square u3 by dx2 square plus p equals to 0. This becomes our expression. We need two boundary conditions. So, boundary condition 1 can be that u3 at minus 1 by 2 will be equals to u3 in the second boundary condition plus 1 by 2 is to 0. So, we have this membrane which is fixed at these two ends and this is x is equals to 0, x2 equals to 0. This is minus x2 equals to minus 1 by 2, this is x2 equals to plus 1 by 2. Okay. So, this was our coordinate axis, right, it was E2, E1 and E3. Alright, great. So, x2 is 0. Let us solve this expression. Now, we can first do a normalization. So, let us do a non-dimensional analysis. Okay, where u3 normalized is u3 over some maximum displacement, say this gets displaced to a certain level, say this is A, And then let's take our x2 normalized with this length L, this total length L. This is say L by 2 to L by 2. This total length is L. So, x2 over L, and we can substitute this. So, what we get is mu times A over L square into d square u bar 3 by dx2 bar square plus p is equals to 0. We can take this to the p term and we can say that d square u3 bar by dx2 bar square plus p bar is equals to 0, where p bar is equals to L square P over mu into A. So, this is a normalized pressure term, right. So, P over mu A by L square is a normalized pressure term. Now, this term we can write the boundary condition that U3 bar at minus 1 by 2, again in this case it is L by 2, this is my mistake, as L by 2 equals to U3 bar at plus 1 by 2 is equals to 0. So, we try to integrate this twice, and what do we get is that U3 bar is equals to minus P bar x2 bar square by 2 plus C1 x2 bar plus C2. Now, we have two integration constants and we have two boundary conditions. So, we can substitute our boundary conditions. Let us write down our equation. U3 bar is equals to minus P bar by 2 x2 bar square plus C1 x1 x2 bar plus C2. Okay. If we substitute our constants, our boundary conditions, so substituting the boundary conditions, we get C1 is equals to 0 and C2 is equals to P bar over 8. Therefore, U bar of 3 x2 bar is equals to minus P bar over 2 x2 bar square minus 1 by 4. On renormalizing, U3 for x2 equals to minus PL square by 2 mu A x2 by L whole square minus 1 by 4. Where is the maximum displacement? The maximum displacement is that x is equals to x2 is equals to 0. So, U3 max will be equals to PL square by 8 mu A, okay, and it will be at the center. Let's take up another problem in which we are looking at the membranes with a concentrated load. So, this membrane with a concentrated load is that now in the last case this membrane we had a distributed load, right. So, we had a distributed load. Now, let us take a concentrated load case in which the same membrane we can draw, and let us say that we have a concentrated load at some point x naught. Okay, so, for a concentrated load or a point load, so a point load, how can it happen? It can be induced by some actuating mechanism. Okay. So, you can have some say for example AFM, right. So, the needle is very sharp and it is scanning across the surface and it is spinning and it is pointing at different directions. So, that is a point load. So, the tweezer is controlled by some electrical impulse or some magnetic impulse. So, it is called an electro or a magneto actuating device, it is actuating system, right. The point source will be modeled using the Green's function operator. Okay. The equation for Green's function operator, del square g by del x square plus del x minus x naught equals to 0, where this del is the Dirac delta function. What does this do is that if this is our coordinate system, this is 0 and this is 1, then at given x naught, this value is equals to 1. So let's write it again. X equals to x naught. So this is our del x minus x naught. This is y and this is x. Okay. So we are having 1 at the point of the load, and then we have to solve everywhere it is 0. So with that property, so the solution of this function, of this expression, is called the green function. Okay. So what we have is that g of minus 1 by 2 equals to g of plus 1 by 2 equals to 0. That was our boundary condition. So our domain is between minus 1/2 to plus 1/2 as for our stretch string. Then how do we solve this? The first thing is that we will use the property of the Dirac delta function. We know that this d squared g by dx square equals to 0. This Dirac delta is 0 everywhere if our domain is x is not equals to x naught. The solution for this, if we integrate it twice, g of x will be equals to ax plus b and cx plus d for minus half to x naught, not including x naught, and x naught to 1 by 2. Okay. If we impose our condition, impose g of plus minus 1 by 2 equals to 0, we get gx equals to ax plus 1 by 2 c x minus 1 by 2. So this is minus 1 by 2 to x naught, this becomes x naught to 1 by 2. Okay. Now we need to find the other two integration constant. Since we are almost over time, let us stop over here. We will pick this up in the next lecture from this expression, and then we will continue on towards ending the membranes and going in towards beams or thick plates in which we have this bending effect added up to our deformations, axial deformations. Thank you for listening today, and we will meet in the next lecture. Thank you.